Hi folks, this is week 6 of Beginning Web Databases, and this week we're talking about database design. The reading for this week is chapter 6 of the Larry Ullman book. So let's begin by discussing anomalies and normalization. Normalization is making a database normal. It means we're going to go into our database and reduce redundant data. Redundant data that can cause something called an anomaly. This isn't going to make sense to you at first as it's a very foreign concept. Let's dive in. Oops. So basically, any table that has redundant data may have problems known as this anomaly. Data redundancy is the cause of any anomaly. Redundancy is the duplication of data that causes anomalies. So let's look at some examples. There are 3 types of anomalies. The first is when we make an insertion into a record without having it stored on a related record. When 2 tables are dependent on each other, and you need to see an example of that as soon as possible, but when you insert a record without having it stored in the related record, that means there's an insertion anomaly. Data goes into one table when it should be in the other. A deletion anomaly is when you delete some information and lose any related information at the same time. An update anomaly is any change you make to your data that requires you to scan every record to make sure that changes happen multiple times. So let's focus on the first one, an insertion anomaly. This occurs when certain attributes cannot be inserted into the database without the presence of another attribute. So let's take a look. In this case, we have one table. We have a course number, a list of tutors, some rooms, a room size, and a limit. If we build a new room, B123, but it doesn't have any course or members or staff information, we would have an insertion anomaly. We could put the room B123 in there, but the other fields would be empty. The course number would be empty, the tutor would be empty, and the room size and limit would probably be empty. But we know at least if we make an insertion anomaly into our database for a school, and we have a table that is maybe, we could call it room schedule. When we insert this new room, if we don't insert for course number and tutor, we'll have an insertion anomaly. We'll have an empty set. And what might happen later is that when we add the course number or the tutor, that it gets entered into a separate entry that doesn't relate to the room size, or the limit. If you read the chapter and understand what the word entity means, we have 2 entities here. We have one called courses and one called room, basically rooms. So when we have 2 different entities in one table, we leave ourselves open for duplicate data. If I were to put this into a building table or a room table and then a schedule table, then we could use primary keys or foreign keys to ensure that there was no duplicate data. But right now, we just want you to learn the insertion anomaly, which means that we might have some empty data in here for a little bit if we just insert information about the room. So a delete anomaly exists when certain attributes are lost because of the deletion of other attributes. So let's take another look at our table here. We've got our schedule table again with course numbers, tutors, and the room information. But if we remove course number 351 from the above table, all the details from room C320 would get deleted as well. So that means that any corresponding course that has C320 would also get deleted. So think about this. The fact is that we have this room and we have information about this room. We know its size and we know its limit. Well, if we delete course number 351 here and delete that entire record, all the data that relates to the room will be gone. And that is a deletion anomaly. That means all the other courses that might use room 320 would lose that data. So we only want to delete information about the course. Again, by creating 2 entities off this table, one for courses and one for building information, we would have two tables, and then we could delete the one record on the course number without affecting the information about the building. The third, the update anomaly, needs an example as well. So an update anomaly exists when one or more instances of the duplicate data is updated but not all. So let's take another look at this. We have the same unnormalized table here. It's not even in the first normal form. And let's say room H940 has been improved, and now it has 500 people capacity. It's a big room, and we have two courses that depend on it. So if we update a single entity, we would have to update all the other columns where the room is H940. So let's say we updated the course number 355 and changed the room size to 500. Unfortunately, we'd also have to update that fourth record as well. So because, again, there are two separate entities here inside one table, we have the risk of an update anomaly. The fact is we might update one record and leave the other records to not be updated at all. So what do we have to do about this? Well, we have to normalize the table. This is the process of putting things right. Basically, in a relational database, it has specific mathematical meanings that concern separating elements of data, names, addresses, into what people call affinity groups, or also entities, and defining the right relationships between them. This is a database technique which organizes tables in a manner that reduces any redundancy and dependence of data. So normalization is a strict standardized rule for making a database. And I've already hinted at the previous table and how it might be normalized. But let's take a look. We could do it in any number of levels. The first normal form is the simplest way to reduce our redundancies and to reduce our risk of anomaly. So the requirements for the first normal form is that each and every table has a primary key, similar to what I've been making you do in the first couple of homework assignments in the database section of this course. So basically every table would have a key and a minimal set of attributes which can uniquely identify a record. So if we go back and look at our previous tables, I'm going to go back real quick, we might see one table for the left two fields, and that might have an ID. So let's say that it was just called a table called courses. I may have an ID for 1, 2, 3, and 4. And then I might have another table for room size, and limit, but also have an ID primary key on that one as well. So let's go back to that slide on first normal form. We need to make sure that each values in the table are atomic, so no multi-value attributes are allowed. Basically one piece of data only. So no multiple values, no comma separated values, nothing like that. We also need to make sure that there are no repeating groups. We want the simplest piece of data possible in each and every field. So the repeating groups simply means that two columns do not store similar information in the same table. So in our case on room number, we might not want to have, I'm going to go back a little bit, we might not have a second field here with a similar room size. So that is the first normal form, but let's take a look at an example. So in an unnormalized students table, this is a perfect example. I have a student number, and you see it's a primary key here, and we have another ID, a name, room, class 1, and class 2. Well, what's not normalized here is the fact that when we have class 2 and class 1, those could be separate tables. So let's take a look at normalizing that. We make it a separate record. So look, we have a class number, but not specific to 1 and 2. So we have student number, more ID information, who the student is, the room that he has the class, and the class number itself. Now, this is first normal form, but what we did was remove something that was very specific to the class that would require separation. Now, with the first normal form, we've improved a little bit. However, we have still some duplicate data here. So let's look at the second normal form. That's the next level of reducing our duplicity or redundant values. So the requirements for the second normal form, of course, the requirements for the first normal form must be met. but the redundant data across multiple rows of table must be moved to a separate table. Now this is most of the databases in web. We have the redundant data here. We have student IDs that are redundant, advanced IDs, advanced names, advanced room, all these things are redundant. These need to be moved to a separate table. So what happens is the resulting tables have to be related to each other by use of a foreign key. Well, you can also do it with a primary key, but you lose the foreign key constraints. If you're curious about that, just find the part of the text where it discusses it, and I'll also do a video on it. But you can only use a foreign key with an InnoDB data type. The MyISAM will work with primary keys, but you can still have a deletion anomaly. That's an important concept. So let's move forward with using the InnoDB and foreign key constraints until you get the hang of how it works. So this is an example of the second normal form. And now we've really reduced our redundancies. We have student information. We have the registration table. So right here we have student 123, and here's student 123 in their class. And because it's a number, it's going to work a little faster. So now I can see that student 123 also has this class number, and student 124 has 2090 and 1028. Now part of what we'll do in Chapter 7 next week is create multiple table queries, learn how to do SQL to call the data. So if we wanted to call all the classes that James was in, we could call both tables. Now what's missing here, actually it's not missing, this is the primary key here, so you would do it where the IDs are equal, but second normal form is where you'll see the bulk of the web applications, including the applications you see in our text. So the third normal form is similar to the second in that the previous normal form must be met. But now we have to eliminate any fields that don't depend on the primary key. So any field that is dependent, not only on the primary key but also on another field, must be moved to another table. So let's take a look at that now. Now we have a third advisor table. We have the student table, the registration table, and now the advisor ID has moved back. So now the advisor ID is the third table, and he's 123, his name is James, and that's his room. So the class, if you look here, the student number and the class number are not related to anything but the primary key. So everything relates to its own primary key here, whether it's the advisor ID or this section here. So in this case, we have a holder table that connects both, and that's the third normal form. So what we just discussed was a bit about anomalies and a little bit about normalization. There's much more to come, but you'll see some examples in e-commerce. You just need to look at examples on this to get a good hang for it. But I would focus definitely on the second and third normal form. The second is still good because everything relates, but when you know that these are advisors, it's separate into the third table. So this is where we get a much better, much faster database.